Our planet is dominated by water, with oceans covering more than 70% of its surface. Yet beneath these rolling waves lies a realm that remains largely unexplored and enigmatic, a world that challenges the very boundaries of our understanding of life. Imagine descending into a place where sunlight is forever absent, where the only illumination comes from the faintest glimmers of bioluminescence or the slow drift of marine snow. This is a domain of perpetual twilight, fading rapidly into utter blackness as depth increases. The deep sea is the largest habitat on Earth, yet it is also the least accessible. Its vastness is matched only by its mystery, stretching for thousands of kilometers and plunging to unimaginable depths. The descent begins at the edge of the continental shelf, where the last rays of sunlight are filtered and scattered, giving way to a world where darkness reigns supreme. Here, the ocean transforms from a sunlit expanse to a cold, forbidding abyss. At the heart of this abyss lies the Mariana Trench, the deepest known part of the world's oceans. This immense chasm stretches over 2,500 kilometers in length and reaches a depth of nearly 11,000 meters at its lowest point, Challenger Deep. To put this in perspective, if Mount Everest were placed at the trench's bottom, its summit would still be submerged beneath more than a kilometer of water. The environment here is nothing short of extreme. Temperatures hover just above freezing, rarely rising above 2 degrees Celsius. The seafloor is a barren, desolate landscape, punctuated by occasional hydrothermal vents and cold seeps, but otherwise devoid of the features familiar to shallower waters. Life in the Mariana Trench must overcome a gauntlet of formidable challenges, each more daunting than the last. The first is the near-total absence of light, which renders photosynthesis impossible and forces organisms to adapt to a world without vision or color. Food scarcity is a constant threat. With no sunlight to fuel plant life, the only nourishment comes from organic particles, marine snow, that drift down from the surface or from the occasional carcass of a large animal that sinks to the depths. These rare feasts are quickly consumed by opportunistic scavengers. The cold is relentless. Water temperatures remain just above freezing, slowing metabolic rates and forcing creatures to conserve energy. Many deep-sea animals move slowly, their bodies adapted to function efficiently in the frigid environment. In certain isolated pockets, hypersaline brine pools form, their salt concentrations so high that they create underwater lakes. These brine pools are lethal to most forms of life, and only the most specialized organisms can survive at their margins, where chemical gradients are steep and toxic. The most defining feature of the trench is the immense pressure. With every 10 meters of descent, the pressure increases by 1 atmosphere, reaching over 1,000 times the atmospheric pressure at sea level at the trench's deepest point. This pressure is so intense that it would crush most conventional materials and obliterate unprotected life forms. Despite these overwhelming obstacles, life persists. The organisms that inhabit the Mariana Trench are unlike any found elsewhere, having evolved extraordinary adaptations to survive in this alien environment. For centuries, the trench was thought to be devoid of life, a sterile void too hostile for even the hardiest of organisms. The absence of sunlight, the scarcity of food, and the crushing pressure seemed insurmountable. However, advances in deep-sea exploration have shattered these assumptions. Remotely operated vehicles and submersibles equipped with powerful lights and cameras have revealed a thriving, if sparse, ecosystem. The deep sea is home to a remarkable diversity of life, from translucent amphipods and giant single-celled xenophyophores to predatory fish and bioluminescent invertebrates. Each species is a testament to the power of adaptation. Many deep-sea creatures possess features that seem almost otherworldly: enormous jaws, needle-like teeth, expandable stomachs, and organs that emit light. These adaptations are not random. They are precise solutions to the challenges of darkness, scarcity, and pressure. Some animals have evolved bodies with minimal calcification, allowing them to withstand the crushing pressure by remaining flexible. Others have developed unique enzymes and cellular structures that prevent their proteins from denaturing under extreme conditions. The resilience of these organisms is extraordinary. They thrive in an environment where energy is scarce, temperatures are near freezing, and the pressure is relentless. Their existence demonstrates the remarkable plasticity of life. Exploring the Mariana Trench is not merely a journey into physical depth, but a journey into the extremes of biology and chemistry. Each layer of the trench presents new challenges and new forms of adaptation. The creatures found here often appear more alien than anything on land. Their forms and behaviors are shaped by millions of years of evolution in isolation, resulting in species that defy conventional classification. Some organisms have gelatinous bodies that simply yield to the pressure, while others rely on chemosynthesis, harnessing chemical energy from hydrothermal vents or methane seeps to survive in the absence of sunlight. As we descend, layer by layer, past the last vestiges of light, we enter a world defined by cold, darkness, and pressure. Here we encounter the true limits of life on Earth, a testament to the adaptability and resilience of living organisms in the face of the most extreme conditions imaginable. In the sunlit upper layers of the ocean, life flourishes in a vibrant tapestry of color and movement. Here, the sun's energy powers photosynthesis, fueling a rich food web that supports everything from tiny plankton to massive predators. But as we descend into the abyss, sunlight fades and eventually disappears entirely. In these lightless depths, the rules of survival are rewritten. The deep sea is a realm of perpetual scarcity, where every calorie is precious and the search for sustenance shapes every aspect of life. The primary food source for most deep-sea inhabitants is marine snow, a continuous slow rain of organic debris that drifts down from the productive surface waters above. This marine snow is composed of dead phytoplankton, decaying animal remains, fecal pellets, mucus, and other microscopic detritus. It is the lifeblood of the deep, providing a tenuous link to the sunlit world far above. Each particle is minuscule, but together they form a vital, if meager, supply of nutrients. The deeper one goes, the sparser and more degraded these particles become, forcing deep-sea creatures to adapt in extraordinary ways. In this environment, food scarcity is the norm. The deep sea's pantry is shared by all, but the portions are vanishingly small and competition is fierce. To survive, deep-sea animals have evolved to conserve energy with remarkable efficiency. Many species move with deliberate slowness, their metabolisms slowed to a crawl to stretch every calorie as far as possible. Some, like the grenadier fish and certain amphipods, can go weeks or even months between meals, relying on stored fat reserves and a slow pace of life. Every movement is calculated, every action measured. Wasting energy can mean the difference between life and death. The vampire squid is a master of this energy-saving lifestyle. Dwelling at depths around 3,000 meters, it occupies the oxygen minimum zone, where few predators can survive. Unlike active hunters, the vampire squid is a passive feeder, rarely expending energy in pursuit of prey. It extends two long, sticky filaments into the water, which act as passive traps for drifting particles. These filaments collect marine snow and other organic debris, functioning much like flypaper in the darkness. When enough material has accumulated, the squid reels in its filament, scrapes off the gathered particles, coats them in mucus, and forms a compact food ball to eat, an ingenious adaptation to a world of scarcity. Other deep-sea animals have evolved even more specialized feeding strategies. Some, like certain polychaete worms, extend feathery appendages to filter tiny particles from the water, while others, such as sea lilies, use sticky arms to trap passing detritus. The giant lavacean, a small tadpole-like animal, constructs an elaborate mucus house that can reach over a meter in diameter. This intricate structure acts as a highly efficient filter, capturing particles as small as bacteria and single-celled algae. By beating its tail, The larvacean pumps water through its mucus house, trapping food that would otherwise be inaccessible to larger animals. When the filter becomes clogged, the larvacean abandons it, letting the nutrient-rich structure sink to the sea floor, where it becomes a valuable meal for bottom-dwelling scavengers. On the vast abyssal plains, thousands of meters below the surface, creatures like the gummy squirrel sea cucumber employ a different approach. These animals act as the ocean's janitors, methodically sifting through the fine sediment to extract organic matter that has settled after its long journey from above. The gummy squirrel's elongated, tail-like appendage can be raised into the gentle currents, maximizing its ability to sense and exploit new feeding grounds. This tail acts as a sail, allowing the animal to harness even the faintest water movement to glide across the seafloor, searching for untouched patches of nutrient-rich mud. Foraging in the deep is a slow, methodical process. Many animals, such as brittle stars and certain crustaceans, roam the seafloor in search of organic fragments, sometimes traveling great distances for a single meal. Occasionally, a rare windfall arrives in the form of a whale fall, a massive carcass that sinks to the bottom, providing a sudden, rich banquet for a host of scavengers. Amphipods, hagfish, and sleeper sharks converge, devouring the soft tissues and leaving only bones behind. Even the bones are not wasted. Specialized bone-eating worms, known as ossidacs, bore into the skeleton, extracting fats and nutrients inaccessible to other creatures. In some regions, life is supported by chemosynthesis rather than photosynthesis. Around hydrothermal vents and cold seeps, bacteria convert chemicals like hydrogen sulfide or methane into energy, forming the base of unique ecosystems. Giant tube worms, clams, and mussels host symbiotic bacteria within their bodies, allowing them to thrive in these otherwise inhospitable environments, independent of sunlight or marine snow. Predation also plays a role in the deep. Some fish, like the anglerfish, use bioluminescent lures to attract unsuspecting prey in the darkness, while others rely on stealth and camouflage to ambush passing animals. The gulper eel, for example, can unhinge its massive jaws to engulf prey much larger than itself, an adaptation to the unpredictability of food availability. Scavengers, from giant isopods to amphipods, are ever vigilant, ready to exploit any organic material that reaches the seafloor, ensuring that nothing goes to waste. Even gelatinous animals like deep-sea jellyfish and siphonophores have evolved specialized tentacles and stinging cells to capture the rare prey that drifts within reach. Bioluminescence is a common adaptation, used not only for hunting but also for luring prey, confusing predators, and communicating in the darkness. In this world of perpetual night, survival depends on a combination of patience, efficiency, and remarkable ingenuity. Every organism, from the smallest microbe to the largest scavenger, plays a role in the deep sea's intricate web of life, making the most of every scrap of food that the ocean provides. In the perpetual darkness of the deep ocean, sunlight never penetrates. Most life here depends on a slow rain of organic debris, marine snow, drifting down from the sunlit surface. But in the deepest trenches, even this meager supply is scarce, and survival demands extraordinary innovation. Yet scattered across the abyssal plains are vibrant oases, ecosystems that have severed their ties to the sun entirely. Here, life flourishes in complete darkness, drawing energy from the earth itself. At the heart of these ecosystems are chemosynthetic bacteria. Unlike plants and algae, which use sunlight to power photosynthesis, these microbes harness chemical energy from compounds like hydrogen sulfide and methane which gush from the planet's crust. In the utter blackness, these bacteria perform chemosynthesis, transforming toxic chemicals into usable energy. This process forms the foundation of entire food webs, supporting creatures that would otherwise have no hope of survival. Around these vents, life gathers in astonishing abundance. Giant tube worms, ghostly white crabs, and swarms of shrimp thrive in the mineral-laden waters, each adapted to the extreme conditions. Hydrothermal vents, often called black smokers, are like underwater geysers. They form where seawater seeps into the crust, is superheated by magma, and erupts back out, loaded with dissolved minerals and chemicals. These vents build towering chimneys of metal sulfides, some reaching tens of meters high. The water they emit can exceed 350 degrees Celsius, hot enough to melt lead. Yet life persists right at the edge. The creatures here have evolved remarkable adaptations. Some shrimp have light-sensing organs on their backs to detect faint heat from the vents, while others host chemosynthetic bacteria within their bodies, forming intimate symbiotic partnerships. One of the deepest known vent fields, Ashadze 1, lies over 4,000 meters down on the mid-Atlantic ridge. Here, the pressure is immense and the darkness absolute. Among the most extraordinary inhabitants is the Pompeii worm. This creature endures temperatures up to 80 degrees Celsius, hotter than most animals can survive. The worm anchors its tail in the scalding vent water while its head remains in cooler currents. This unique positioning allows it to exploit both extremes, a feat unmatched in the animal kingdom. Its secret weapon is a thick fleece of symbiotic bacteria coating its body. These microbes not only insulate the worm from heat, but may also detoxify harmful chemicals, creating a living shield. Not all chemosynthetic habitats are so violent. Cold seeps are quieter, more stable environments where gases like methane and hydrogen sulfide seep gently from the seafloor. These seeps can last for thousands of years, supporting communities of clams, mussels, and tube worms that grow slowly but live for centuries. Here, methane bubbles rise silently from the mud, providing a steady supply of energy-rich chemicals for chemosynthetic bacteria. These bacteria metabolize methane, producing calcium carbonate as a byproduct. Over time, this builds up into rocky reefs that provide shelter for countless organisms. Giant tube worms dominate these seeps, forming dense forests that sway in the deep currents. Some individuals reach lengths of over 2 meters. Lacking mouths and digestive tracts, these worms rely entirely on internal symbiotic bacteria to convert chemicals into food, a partnership so complete that the worms cannot survive without their microbial tenants. Occasionally, a massive influx of nutrients arrives in the form of a whale fall. When a whale dies and sinks, its carcass becomes a banquet for deep-sea life. The arrival of a whale fall transforms the barren seafloor into a thriving ecosystem, supporting hundreds of species for decades as the carcass is slowly consumed. Scavengers like hagfish and rat-tail fish are the first to arrive, stripping flesh from the bones in a matter of months. Their activity paves the way for a succession of ever more specialized organisms. As the soft tissue disappears, new colonizers move in, creatures uniquely adapted to feast on what remains. Among the strangest are the Osedax, or zombie worms. These bizarre animals have no mouth or stomach, yet they thrive by boring into the bones themselves. Osedax worms secrete acid to dissolve bone, sending root-like extensions deep inside. Within these roots, symbiotic bacteria break down fats and oils, nourishing the worm in a partnership found nowhere else in the animal kingdom. In these sunless realms, life has evolved to exploit every available resource, forging alliances with microbes and mastering the art of survival in the most extreme environments on Earth. The deep sea's chemosynthetic worlds are a testament to the ingenuity and resilience of life, thriving where sunlight never shines. Beyond the scarcity of food and the crushing pressure, life in the deep must also contend with a constant penetrating cold. In the Mariana Trench, temperatures rarely rise above 1 to 4 degrees Celsius, creating an environment where only the most specialized organisms can survive. In the abyssal and hadal zones, the water temperature hovers just a few degrees above freezing, a condition that dramatically slows down all metabolic processes. This means that every heartbeat, every movement, and every chemical reaction inside these creatures is slowed to a crawl. For many animals, this extreme cold is not just a challenge to be overcome, but a defining feature of their existence, shaping their size, their lifespan, and their very biochemistry. Deep-sea amphipods, for example, have evolved enzymes that remain flexible and active at low temperatures, allowing them to digest food and repair cells even in the coldest depths. In the frigid, oxygen-rich waters of the polar regions and the deep sea, we see a phenomenon known as polar gigantism, where some species grow to sizes far exceeding their relatives in warmer waters. This is partly due to the increased solubility of oxygen in cold water, which supports larger body sizes. One striking example is the Antarctic sea spider, but in the trench, amphipods and isopods also display remarkable size, with some species reaching lengths of over 30 centimeters. While most sea spiders and amphipods are small, inconspicuous creatures, these deep polar and trench giants can have leg spans or body lengths many times greater than their shallow water cousins, making them hundreds of times larger than their relatives in warmer, shallower seas. The cold water slows their metabolism to a glacial pace, reducing the need for food and allowing them to survive on the sparse resources available. This slow metabolism also means that many deep-sea organisms can live for decades or even centuries, with some corals and sponges in the deep estimated to be thousands of years old. Furthermore, cold water holds more dissolved oxygen than warm water. This abundance of oxygen makes it easier to supply a large body with the fuel it needs to live, supporting the slow but steady lifestyles of trench dwellers, allowing these animals to reach proportions that would be impossible in a warmer, less oxygenated environment. Their slow, deliberate movements are a perfect adaptation to a life where energy must be conserved at all costs. Living in water that is perpetually on the verge of freezing presents another critical problem: the formation of ice crystals within an animal's body, which can rupture cells and prove fatal. To survive, trench organisms have evolved unique biochemical defenses. Many fish in these environments have evolved a remarkable biological tool: antifreeze proteins. The new thenioid fish, which make up the vast majority of fish biomass in the Antarctic, and some deep-sea snailfish, are masters of this adaptation. These special proteins circulate in their blood and bind to any tiny ice crystals that begin to form. By attaching to the crystals, the proteins prevent them from growing larger, effectively stopping the freezing process in its tracks and allowing the fish to survive in water that is technically below the freezing point of their own bodily fluids. This adaptation is so effective that some trench fish can remain active even as the water temperature dips below zero. Perhaps the most extreme adaptation to the cold and oxygen-rich deep is seen in the crocodile icefish, but trench amphipods and snailfish also display unique physiological traits. The crocodile icefish is the only known vertebrate in the world to have clear blood, as it completely lacks hemoglobin, the protein that carries oxygen in red blood cells. Some deep-sea snailfish have also evolved blood with reduced hemoglobin, relying on the high oxygen content of cold water. In the frigid, highly oxygenated Antarctic and trench waters, these fish have adapted to absorb oxygen directly from the water, sometimes even through their skin. They possess large, feathery gills and thin, scaleless skin to maximize oxygen absorption. To compensate for the lack of oxygen-carrying proteins, these animals have a much larger heart and a greater volume of blood than other fish, allowing them to pump a sufficient amount of dissolved oxygen throughout their bodies, even in the coldest, deepest waters. These radical and unique solutions, ranging from antifreeze proteins to specialized enzymes and circulatory systems, are what allow life to persist in the deep freeze of the Mariana Trench, where only the most extraordinary adaptations can ensure survival. As if the darkness, hunger and cold were not enough, the deep sea holds another, stranger peril: underwater lakes of brine. These brine pools are bizarre and deadly features found on the seafloor, where deposits of salt from ancient dried-up seas have dissolved into the water, creating depressions filled with liquid that is 3 to 8 times saltier than the surrounding ocean. This hypersaline water is also incredibly dense, and because it does not mix with the seawater above, it forms a distinct shoreline and surface. These pools are also anoxic, meaning they contain no oxygen. For most marine animals, accidentally swimming into a brine pool is a death sentence, as the extreme salt content causes a fatal osmotic shock, rapidly drawing all the water out of their cells. These pools create an eerie, otherworldly landscape on the seafloor. Scientists have observed crabs and other crustaceans that have wandered into the brine, where they are instantly pickled and preserved, their bodies lying perfectly intact on the bottom for years. The surface of the pool shimmers like a mirage, a clear boundary between life and a toxic, lifeless lake. The contrast is stark and immediate. The area surrounding the brine pool may be teeming with life, such as mussels that thrive on the methane seeping from the pool's edges, but the pool itself remains a sterile, forbidding trap. It is a powerful reminder of the delicate chemical balance required to sustain life, and how easily that balance can be disrupted. Yet, even in this most toxic of environments, life finds a way. The chemistry of brine pools is complex. The high concentration of dissolved salts, primarily sodium chloride and magnesium chloride, creates a dense, stratified layer that resists mixing with the overlying seawater. This sharp boundary, known as a halocline, marks a dramatic shift in salinity and density. At the very edge of these pools, unique microbial mats flourish. These bacteria and archaea are specially adapted to survive in hypersaline, anoxic conditions, using chemosynthesis to convert methane and hydrogen sulfide into energy. Some brine pools are bordered by colonies of tube worms, which rely on symbiotic bacteria living inside their bodies. These bacteria process the chemicals seeping from the brine, providing nutrients for their hosts in a partnership found nowhere else on Earth. Amphipods and other small crustaceans can sometimes be found skirting the edges, feeding on organic matter and microbial mats, but never venturing into the deadly brine itself. The only known vertebrate capable of not only surviving but thriving within a brine pool is the Gulf hagfish. This primitive eel-like creature has developed a suite of incredible adaptations that allow it to venture where no other fish can go. Its primary defense is its famous slime. When threatened or stressed, the hagfish can excrete a thick, gelatinous mucus that, upon contact with the salty water, expands to up to 10,000 times its original volume. It is thought that when entering a brine pool, the hagfish coats its body in this slime, which acts as an insulating barrier, reducing the exchange of water between its body and the hypersaline environment. This protective slime coat effectively shields the hagfish from the deadly osmotic shock that would kill any other fish. In addition to this physical barrier, the hagfish also possesses an unusually high tolerance for low oxygen conditions, allowing it to hunt for food within the anoxic brine for short periods. It can venture into the deadly lake to scavenge on the unlucky creatures that have perished there, turning the lethal trap into its own private larder. The hagfish's gills are specially adapted to extract what little oxygen is available, and its metabolism can slow dramatically, allowing it to survive in conditions that would suffocate most other animals. The chemistry at the brine pool's edge is dynamic, with minerals precipitating out of solution and bubbles of methane and hydrogen sulfide rising from the sediment, fueling entire ecosystems based on chemical energy rather than sunlight. Some microbes near brine pools are even bioluminescent, producing faint glows in the darkness, possibly as a way to attract prey or communicate in the pitch-black depths. The hagfish's ability to conquer the brine pool is a stunning example of evolutionary problem-solving, showcasing a unique creature that has mastered an environment so extreme it serves as a barrier to all of its competitors and predators. Brine pools are a testament to the diversity of life and the power of chemistry in shaping the boundaries of existence. In these alien lakes, the rules of survival are rewritten, and only the most extraordinary adaptations allow life to persist. Of all the challenges in the deep sea, none is more pervasive or more powerful than the crushing pressure. The deeper you go, the more relentless and unforgiving this force becomes, shaping every aspect of life in the abyss. For every 10 meters you descend, the pressure increases by 1 atmosphere, the equivalent of the air pressure we feel at sea level. But in the deep, this adds up quickly, creating an environment that would obliterate most surface life. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure is over 1,100 atmospheres. That's more than a ton of force on every square centimeter. This is akin to having the weight of a large truck balanced on your fingertip. Any air-filled space would be instantly crushed, and even the strongest materials are tested to their limits. Such immense force would instantly implode any air-filled spaces, like lungs or a swim bladder, and it fundamentally alters the way biological molecules behave. Life here must adapt at every level, from the largest animal to the tiniest molecule. For life to exist here, it must be built differently from the ground up, designed not to resist the pressure, but to yield to it. This means rethinking the very architecture of living things. The most obvious adaptation is in the body structure of deep-sea creatures. Instead of rigid skeletons, many have evolved soft, pliable bodies that can withstand the crushing force by simply flowing with it. Animals like the Dumbo octopus, which holds the record as the deepest living octopus at 7,000 meters, have bodies that are almost entirely water, with no rigid bones to break or collapse. The mysterious bigfin squid, too, is built without hard, rigid skeletons. Their bodies are soft, gelatinous, and composed almost entirely of water. This unique composition allows them to maintain internal pressure equal to the crushing force outside, eliminating any dangerous pressure differential. Because they have no internal air pockets to be crushed, the pressure inside their bodies is the same as the pressure outside. This equilibrium is the secret to their survival. They are in perfect balance with their environment, their bodies shaped and supported by the very force that would destroy most other life. This is why deep-sea animals brought to the surface often look like deflated, blob-like messes. Their bodies are structured to be supported by the immense pressure of the deep, and they cannot hold their shape without it. In their natural habitat, these animals are perfectly formed, their bodies sculpted by the invisible hand of pressure. Remove that support, and their delicate structures collapse, unable to withstand the absence of pressure. But the battle against pressure isn't just fought at the macroscopic level. At the microscopic scale, cells themselves must adapt to survive. High pressure can force cell membranes, which are made of fatty lipids, to become rigid and waxy, preventing them from functioning correctly. This rigidity can block essential processes, threatening the very survival of the cell. To counteract this, deep-sea organisms have evolved cell membranes with a high proportion of unsaturated fats. These fats have kinks in their molecular structure, preventing tight packing and keeping membranes fluid. These fats are more fluid and less prone to being compressed and solidified by the pressure, ensuring that the membranes remain flexible and permeable, allowing essential nutrients to pass in and out of the cell. This flexibility is vital for cellular survival, enabling deep-sea life to maintain the delicate balance of chemicals needed for life. Creatures like the sea pig, a type of sea cucumber that plods along the abyssal floor, are masters of this biochemical adaptation, maintaining cellular integrity under thousands of atmospheres of pressure. Their cells remain healthy and functional, even as the pressure outside would destroy most other forms of life. Even more critically, extreme pressure can cause the complex three-dimensional structures of proteins to collapse or denature, rendering them useless. Proteins are the workhorses of the cell, acting as enzymes that catalyze all of life's essential chemical reactions. If these proteins lose their shape, life itself grinds to a halt. Deep-sea organisms have evolved remarkable strategies to protect these vital molecules. To protect these vital molecules, deep-sea fish have evolved a chemical stabilizer called trimethylamine N oxide, or TMAO. This small organic molecule works to counteract the distorting effects of pressure, holding proteins in their correct functional shape. TMAO acts as a molecular bodyguard surrounding proteins and preventing them from collapsing under pressure. The deeper a fish lives, the more TMAO it accumulates, creating a chemical shield against the abyss. Scientists have discovered a direct correlation. The deeper a fish lives, the higher the concentration of TMAO in its cells. This adaptation is so effective that it sets a hard limit on how deep vertebrate life can survive. In the crushing darkness of the Mariana Trench, survival is an art form, one that demands constant innovation at every scale, from the shape of a creature's body to the chemistry of its cells. Here, life is not just enduring the pressure, but mastering it. The story of TMAO and its role in stabilizing proteins under pressure leads to one of the most fascinating discoveries in deep-sea biology. But the limits of life in the ocean's greatest depths are shaped by more than just chemistry. They're defined by the very geology and physics of the trenches themselves. There appears to be a hard biochemical limit to how deep a fish can live. But this boundary is also set by the crushing pressure, the scarcity of food, and the unique geological features of the Hadal zone. While creatures with gelatinous bodies, like ctenophores and amphipods, can descend to the very bottom of the trenches, their lack of rigid structure allows them to withstand the immense pressure. Fish, as vertebrates, face a unique physiological barrier. Their skeletons and organs must remain functional under pressures that would crush most life forms. The concentration of TMAO needed to counteract the immense pressure increases steadily with depth, acting as a molecular shield for proteins. Scientists calculated that, at a certain point, the adaptations required for survival become self-defeating. The required concentration of TMAO inside a fish's cells would become so high that it would disrupt the fundamental process of osmosis. This creates a theoretical boundary for fish life, a line drawn not just by chemistry, but by the interplay of pressure, salinity, and the trench's geology. Osmosis is the natural tendency of water to move from a less salty environment to a more salty one, across a semi-permeable membrane. Saltwater fish are constantly losing water to the sea around them, and must drink seawater to stay hydrated, relying on specialized gills and kidneys to excrete excess salt. In contrast, freshwater fish are less salty than their surroundings, and must constantly pump out the water that floods into their bodies. The problem for a deep-sea fish is that TMAO acts just like salt in this regard, increasing the internal salinity of their bodies. As a fish goes deeper and accumulates more TMAO to protect its proteins, its internal fluids become progressively saltier. Approaching the salinity of the surrounding seawater and eventually surpassing it. The theoretical limit for fish was calculated to be around 8,200 meters. Beyond this depth, the adaptations that once protected life become lethal. The concentration of TMAO required to survive the pressure would make the fish's cells saltier than the surrounding seawater. This would cause a catastrophic reversal of osmosis, with water flooding uncontrollably into the fish's cells. Water would flood uncontrollably into the fish's cells, causing them to swell and burst, a fatal outcome. Unlike freshwater fish, deep-sea fish have not evolved the energy-intensive mechanisms needed to pump out massive amounts of excess water. Their slow, energy-conserving metabolisms make such a system impossible. Every adaptation is a trade-off, and in the deep, energy is the most precious resource. Therefore, at approximately 8,200 meters, a line is drawn in the ocean, a frontier that vertebrate life cannot cross. Below this depth, the chemistry required to withstand the pressure becomes incompatible with the chemistry required to maintain water balance. It is a fundamental biological checkmate, dictated by the laws of physics and the geology of the trench. No vertebrate has found a way around this impasse. Instead, the deepest realms are ruled by invertebrates, whose bodies are uniquely suited to the crushing dark. These invertebrates thrive where fish cannot, using flexible bodies, unique cell chemistry, and sometimes even symbiotic bacteria to survive. For years, the deepest living fish known to science was the Mariana snailfish, a small tadpole-like creature found living happily at depths of around 8,000 meters. Its body is soft and nearly transparent, with minimal bone and specialized enzymes that function under extreme pressure. Then, in 2023, scientists filmed another species of snailfish in the Izu-Ogasawara Trench at an astonishing depth of 8,336 meters. This observation is incredibly close to the predicted biological limit, confirming the accuracy of scientific models. It suggests that these snailfish are living on the absolute precipice of what is possible for a vertebrate animal. Below this snailfish frontier, the ocean becomes a world of invertebrates and microbes. In the deepest 25% of the ocean's volume, fish vanish entirely, replaced by creatures with bodies built for the abyss. Here, the reign of fish appears to be over, and the true masters of the deep are those who have adapted in ways vertebrates never could, by yielding to the pressure rather than resisting it. In the deepest reaches of the Hadal zone, places like the Challenger Deep at the very bottom of the Mariana Trench, fish are entirely absent. But this absence is not a sign of lifelessness. Instead, it marks the beginning of a world shaped by forces almost unimaginable at the surface. Here, the environment is defined by crushing pressures over 1,000 times greater than at sea level, temperatures barely above freezing, and a perpetual, absolute darkness. Fish, with their complex organ systems and delicate biochemistry, simply cannot withstand these extremes. The pressure alone would destroy their cells, and the lack of sunlight means no photosynthesis, no plants, and a food web built entirely on what drifts down from above. Yet, life here has found astonishing ways to adapt. Invertebrates and single-celled organisms dominate, each uniquely equipped to survive where vertebrates cannot. The seafloor, far from barren, is alive with creatures that seem almost alien, each one a testament to the power of evolution under pressure. Among the most successful are amphipods, crustaceans that thrive in numbers unimaginable elsewhere. These shrimp-like scavengers swarm any available food, forming dense clouds that can strip a carcass to the bone in minutes. In one scientific expedition, a baited trap left for only a few hours returned with over 200 amphipods, revealing a thriving, densely packed community hidden in the darkness. These Hadal amphipods are giants compared to their shallow water relatives, some reaching lengths of more than 10 centimeters, a remarkable feat in such a hostile environment. Their survival strategies are as unique as their size. They are relentless scavengers, able to detect and consume any organic matter that reaches the trench floor. Unlike fish, amphipods do not rely on high levels of TMAO to stabilize their proteins. Instead, they may possess entirely different, still unknown chemical adaptations that allow their cells to function under immense pressure. Even stranger are the xenophyophores, giant, single-celled organisms that defy our expectations of what a cell can be. Imagine an amoeba, but one that can grow up to 10 centimeters across, its body stretching and shifting as it engulfs particles from the sea floor. These are among the largest single cells on Earth, dwarfing most multicellular animals in the region. Xenophyophores build elaborate skeletons, called tests, from minerals and sediment, creating intricate frameworks that both protect and support their massive cell bodies. These delicate structures are a common sight on the Hadal plains, their fragile forms hinting at the hidden complexity of life in the abyss. To find a single cell thriving at depths beyond 10,600 meters, where the pressure would crush a submarine hull, is a profound testament to the adaptability of life's most basic building blocks. The ecosystem here is fundamentally different from any other on Earth. It is a world where vertebrates have vanished and new forms of life have taken their place. Here, swarms of giant crustaceans and enormous single-celled architects dominate, each filling ecological roles that fish once held in shallower waters. Other invertebrates, like sea cucumbers and bristle worms, have also evolved to thrive in these depths, each with specialized adaptations for a world without fish. Every available niche is filled, from scavengers to filter feeders, each species a unique answer to the challenges of the deep. The line where fish disappear is not the end of life, but the start of a new community, one that has conquered the most extreme pressure on the planet through radical evolutionary innovation. In the deepest dark, life persists, strange, resilient, and endlessly inventive, proving that even where fish cannot go, the story of life is far from over. Our journey from the sunlit surface to the abyssal depths of the Mariana Trench uncovers a realm where life is pushed to its most extreme limits, yet against all odds, it endures and thrives. Here, every organism is a testament to the power of adaptation. In the pitch-black, freezing waters, creatures have evolved extraordinary features to survive. The vampire squid, for example, drifts effortlessly, using its delicate filaments to capture falling marine snow, tiny particles of organic matter that are a precious food source in this nutrient-starved world. The Pompeii worm, meanwhile, forms a living partnership with heat-resistant bacteria, allowing it to thrive on the scalding surfaces of hydrothermal vents, where temperatures can swing from near freezing to over 80 degrees Celsius in moments. In these depths, food is scarce, temperatures are icy, salinity can be toxic, and the pressure is immense, over 1,000 times greater than at the surface. Some animals, like deep-sea sponges and filter feeders, have mastered patience, waiting for the faintest traces of nutrients to drift by. Others have formed bizarre partnerships with chemosynthetic bacteria, harnessing chemical energy from the earth itself, while certain fish produce natural antifreeze proteins to keep their blood from freezing solid. Some deep-sea giants, like the grenadier, move slowly and live for centuries, while others, such as the hagfish, cloak themselves in slime to ward off the corrosive effects of salt and predators alike. The crushing pressure is met not with rigid armor, but with soft, gelatinous bodies and unique chemical stabilizers that keep cells functioning where most life would be destroyed. These adaptations are not just curiosities, they are ingenious solutions to the most daunting challenges nature can offer. At around 8,200 meters, fish reach their absolute limit, unable to survive the overwhelming pressure and chemical constraints. Yet, life does not stop here. Below this boundary, amphipods, tiny crustaceans, flourish in swarms, and xenophyophores, giant single-celled organisms, sprawl across the seafloor, thriving where vertebrates cannot. When one form of life reaches its end, another emerges, perfectly adapted to fill the void, continuing the cycle of survival in the most inhospitable places. Evolution in the trench is relentless, producing creatures with luminous organs to attract prey, jaws that unhinge to swallow meals larger than themselves, and bodies that can withstand the weight of an entire ocean above. As our robotic explorers illuminate these hidden worlds, we discover that the deep sea is not barren, but teeming with life forms that defy our expectations. The biodiversity here is staggering. Each new expedition reveals species never seen before, each with its own story of survival. These creatures are not monsters, but remarkable survivors, our fellow inhabitants shaped by the same evolutionary forces that shaped us. Their existence is a testament to the creativity and tenacity of life, enduring in the deepest, darkest, and most pressurized corners of our world. The story of the trench is one of hope, a reminder that life in all its forms will always find a way, no matter how impossible the odds. As we continue to explore, we are humbled by the resilience of these creatures and inspired by the mysteries that still await us in the uncharted depths of our own planet. Beneath the crushing darkness of the trench, the very water itself is unlike any found elsewhere on Earth. Here, the chemical composition of the abyssal waters forms a complex and ever-changing tapestry, one that both challenges and sustains the life that dares to exist within it. At these depths, the water is infused with an array of dissolved minerals and gases, each playing a crucial role in shaping the ecosystem. High concentrations of magnesium and calcium ions interact with silicates and sulfates, altering the balance of the water and impacting the formation of shells and skeletons. The extreme pressure increases the solubility of gases like carbon dioxide and methane, creating conditions where these compounds can accumulate in unexpected ways. Hydrogen sulfide, a gas toxic to most surface organisms, seeps from hydrothermal vents and cold seeps, providing a vital energy source for chemosynthetic bacteria. These microbes form the base of entire food webs, transforming poisonous chemicals into sustenance for worms, crustaceans, and even giant tube worms. Around brine pools, areas where super salty water collects in dense pockets, the salinity can be 5 times higher than that of ordinary seawater, creating lethal barriers for most forms of life. Yet, specialized extremophiles thrive here, equipped with unique proteins and cellular pumps that regulate their internal chemistry and prevent dehydration. Trace metals such as iron, manganese, and copper are more abundant near hydrothermal vents, precipitating out of the water to form mineral-rich deposits. These metals are essential for the enzymes that power the metabolism of deep-sea organisms, enabling them to utilize chemical energy in the absence of sunlight. Meanwhile, the low levels of dissolved oxygen present a constant challenge. Only the most efficient respiratory systems can function here, and some organisms rely on anaerobic processes to survive. The pH of trench waters can also fluctuate, becoming more acidic near vents and seeps due to the release of carbonic and sulfuric acids. This acidity influences the solubility of minerals and the integrity of biological structures, driving the evolution of protective adaptations, such as acid-resistant shells or gelatinous bodies that lack hard parts altogether. Every drop of trench water is a dynamic mixture, shaped by geological activity, biological processes, and the relentless movement of the ocean itself. For the creatures of the deep, survival means mastering this chemical symphony, adapting to a world where the water is as much a barrier as it is a life support system. It is in this ever-shifting environment that some of Earth's most extraordinary biochemical innovations are found, each one a testament to the ingenuity of life at the edge of possibility. Beneath the crushing waters and swirling chemicals of the Mariana Trench lies a silent record of Earth's most dramatic forces, a geological story billions of years in the making. The trench itself is a product of relentless tectonic activity. Here, the Pacific Plate, one of the planet's largest slabs of oceanic crust, is slowly but inexorably sliding beneath the smaller Mariana Plate in a process known as subduction. This immense collision carves a narrow, crescent-shaped scar into the seafloor, plunging more than 36,000 feet into the planet's crust. Over millennia, layers of sediment have drifted down from the surface, settling silently on the trench floor. These layers are a patchwork of fine silt, volcanic ash, and the skeletal remains of marine organisms, compressed over time into a stratified archive of Earth's changing climate and ocean chemistry. Interspersed within these sediments are unique mineral deposits, including manganese nodules and hydrothermal vent chimneys, evidence of both chemical and volcanic processes at work. The trench walls themselves are marked by steep escarpments, landslides, and fault lines, testaments to the constant motion of the Earth below. Earthquakes ripple through this region as the plates grind and shift, sometimes triggering underwater avalanches that reshape the trench in moments of violent transformation. Hidden within these depths are also rare geological formations, serpentinite mud volcanoes, which bubble up mineral-rich fluids from deep within the crust, and pillow basalts, rounded formations created as molten lava cools instantly in the frigid seawater. These features provide both habitat and chemical resources for deep-sea life, linking geology and biology inextricably. Every fold and fissure of the Mariana Trench is a chapter in the planet's ongoing story, a record of upheaval, transformation, and adaptation. Here, the slow dance of tectonic plates and the patient accumulation of sediment have created one of the most mysterious and dynamic landscapes on Earth, an ancient world still being shaped by the forces beneath our feet. Deep within the Mariana Trench, hidden from sunlight and shielded by miles of crushing water, lie some of the ocean's most extraordinary features, hydrothermal vents. These vents, often called black smokers or chimneys, are towering mineral structures formed where seawater seeps into cracks in the seafloor, encounters hot magma, and is superheated before erupting back out into the abyss. As the scalding water bursts forth, it carries with it a cocktail of dissolved minerals, iron, sulfur, and manganese among them. When this superheated fluid meets the icy cold of the deep ocean, the minerals rapidly solidify, building up the vent's intricate chimney-like walls. Some of these formations can reach heights of over 60 feet, growing and changing as the vent continues to flow. But the true marvel of hydrothermal vents lies not just in their dramatic geology, but in the unique ecosystems they support. In a world where sunlight never penetrates, life here is powered by chemistry instead of photosynthesis. Microbes known as chemosynthetic bacteria thrive in the mineral-rich waters, harnessing the energy from hydrogen sulfide and other chemicals expelled by the vents. These tiny organisms form the foundation of the food web, supporting a cast of remarkable creatures, giant tube worms, ghostly white crabs, and armored snails, all specially adapted to survive the extreme heat, pressure, and toxicity. Hydrothermal vents are islands of life in an otherwise barren landscape, their plumes of mineral-laden water creating oases of warmth and nourishment. These dynamic environments can flare to life and vanish within decades, shaped by the restless geology of the trench. Yet, for as long as they last, hydrothermal vents demonstrate the astonishing adaptability of life, thriving in conditions that would be lethal elsewhere on Earth. In the darkness of the trench, these living chimneys remind us that even in the planet's most hostile environments, nature finds a way to flourish, using the raw materials of the Earth itself to spark new beginnings. Far below the reach of sunlight and far beyond the limits of ordinary life, a hidden army of microorganisms thrives in the Mariana Trench, Extremophiles, the ultimate survivors of our planet. These microscopic life forms have evolved to endure the unthinkable. Temperatures that swing from near freezing to scalding, pressures that would crush a submarine, and a constant bath of toxic chemicals. But how do they do it? The secret lies in their extraordinary metabolic pathways and survival strategies. Instead of relying on sunlight, trench extremophiles use chemosynthesis to convert chemicals like hydrogen sulfide, methane, and even ammonia into energy. Some have specialized enzymes that function only under immense pressure, while others can repair their DNA faster than it can be damaged by the harsh environment. Their cell membranes are reinforced to withstand crushing forces. Their proteins are uniquely structured to resist both heat and cold. Some extremophils form protective biofilms, slippery shields that hold communities together and trap nutrients in the nutrient-poor abyss. These adaptations don't just allow survival, they enable extremophiles to dominate ecosystems where few others can compete. They are the invisible engineers of the deep, recycling nutrients, breaking down toxic compounds and even shaping the chemistry of the trench itself. In the Mariana Trench, extremophiles are a testament to life's ingenuity. They remind us that even in the planet's most unforgiving corners, evolution finds a way, crafting microscopic survivors whose resilience pushes the very boundaries of what it means to be alive. In the silent depths of the trench, where darkness reigns and temperatures plummet, an unseen force is always at work: the deep-sea currents. Though invisible to the eye, these slow, powerful rivers of water shape every aspect of life in the abyss. Unlike the surging tides and crashing waves of the surface, deep-sea currents move with a steady, relentless persistence. Driven by subtle differences in temperature, salinity, and the rotation of the earth, they weave through the trenches like ghostly threads, carrying with them whispers of the world above. For the creatures of the trench, these currents are both highway and lifeline. Nutrients and organic particles, falling from the upper ocean as marine snow, are swept along these underwater flows, delivering vital sustenance to waiting scavengers and filter feeders below. Even extremophiles, those masters of survival, rely on the steady stream of chemical-rich water brought in by these currents to fuel their unique metabolisms. But the influence of deep-sea currents goes beyond nourishment. They sculpt the very landscape of the trench, carving channels in the soft sediment and exposing mineral-rich rocks. As they pass hydrothermal vents, currents disperse plumes of superheated, mineral-laden water, spreading rare elements and supporting entire ecosystems that cluster in their wake. The movement of water also connects distant communities, allowing the larvae of trench dwellers to drift to new territories, ensuring the spread and survival of even the most isolated species. For many, the current is a silent messenger, carrying chemical signals, the promise of food, and the potential for new beginnings. In the stillness of the abyss, deep-sea currents are the pulse that keeps the trench alive. They are the unseen architects of this hidden world, shaping not only its geology, but the delicate balance of life at the very edge of existence. Beneath miles of crushing water, where sunlight never reaches and silence seems absolute, the trench is anything but quiet. Instead, it is alive with a symphony of sounds, subtle, persistent, and utterly alien. This is the soundscape of the abyss, a world where sound travels farther and faster than in air, revealing secrets that light cannot. Here, the walls of the trench reverberate with the deep, resonant groans of shifting tectonic plates, earthquakes and landslides that rumble like distant thunder. Hydrothermal vents hiss and gurgle, releasing jets of superheated water and minerals into the frigid darkness, producing a constant bubbling undertone. Even the slow movement of sediment, stirred by deep-sea currents, adds a faint, ever-present murmur to the background. But it is the trench's inhabitants who turn this soundscape into a living conversation. Many deep-sea creatures are nearly blind, relying on sound as their primary sense. The mysterious clicks and creaks of crustaceans, the eerie, low-frequency hums of fish, and the sharp staccato pulses emitted by squid and other cephalopods all punctuate the darkness. Some species, like the deep-sea dragonfish, produce bioluminescent flashes in sync with bursts of sound, creating a multi-sensory language in the midnight zone. For communication, navigation, and hunting, sound is a vital tool. Whales traveling far above send out powerful, low-frequency calls that penetrate even to these depths, sometimes echoing for hundreds of miles. Meanwhile, smaller organisms use rapid bursts of sound to signal their presence, warn off rivals, or attract mates in the gloom. Even the movement of a predator can be detected as a faint, rhythmic vibration, an early warning in a place where danger is ever present. In this world without light, the ability to hear and create sound is not just an advantage, it is a necessity. The trench's soundscape is a tapestry woven from geology, water, and life itself, a hidden chorus that reveals the unseen rhythms of the deep. Here, in the heart of darkness, every echo tells a story, and every sound is a lifeline. In the perpetual night of the trench, where sunlight never penetrates, life has conjured its own form of magic, bioluminescence. This natural phenomenon, the ability of living organisms to produce light, transforms the abyss into a realm of glowing signals and silent communication. The mechanisms behind this glow are as varied as the creatures themselves. Most commonly, Bioluminescence is the result of a chemical reaction between a light-emitting molecule called luciferin and an enzyme known as luciferase. When these components interact, they release photons, tiny packets of light, illuminating the darkness with eerie blues and greens. Some organisms, like anglerfish, even employ symbiotic bacteria to produce their luminous displays, harnessing the microbes' power for their own survival. But why do these deep-sea dwellers shine? The purposes are as ingenious as they are diverse. For many, bioluminescence is a cloak of invisibility, a tactic called counter-illumination. By matching the faint light from above, creatures like the hatchetfish erase their silhouettes, vanishing from predators below. Others wield light as a weapon. The gulper eel, for example, can flash its tail to distract or confuse attackers, while predatory fish use lures, dangling, glowing appendages, to entice unsuspecting prey within striking distance. Communication is another vital role. Some squid and shrimp emit rapid pulses or patterns of light, signaling to mates or warning rivals in the pitch-black expanse. The stoplight loosejaw, a remarkable deep-sea fish, possesses the rare ability to produce red light, a color invisible to most trench dwellers, allowing it to stalk prey undetected. Even defense becomes an art form in the abyss. When threatened, certain jellyfish and comb jellies unleash cascades of sparkling light, dazzling would-be predators and providing a precious moment to escape. Each glow, flash, and shimmer is a message in the language of the deep. In this world of extremes, bioluminescence is more than a spectacle. It is a tool for survival, a beacon in the void, and a testament to the ingenuity of life in the last true frontier on Earth. In the unfathomable depths of the trench, where day and night are indistinguishable and the sun's warmth is a memory, one might imagine a world immune to the rhythms of seasons and the pulse of global events. But even here, beneath crushing pressures and eternal darkness, the whisper of change is felt. Far above, the turning of the seasons stirs the surface ocean. As spring arrives, plankton blooms erupt in vast clouds, ignited by sunlight and swirling currents. Though these blooms may seem distant, their impact is profound. When surface life dies and drifts downward, it becomes marine snow, a slow, steady rain of organic fragments that nourishes the abyss. Some years the snow thickens, blanketing the trench in a feast. In leaner years, only a sparse dusting reaches the bottom, testing the resilience of those who dwell there. Yet it is not just the seasons that shape this dark world. Global events, invisible to the creatures of the trench, can send shockwaves through their home. A distant volcanic eruption might cloud the skies, dimming sunlight and altering the composition of the falling snow. Shifts in ocean currents, driven by climate cycles like El Niño, can reroute the flow of nutrients, bringing bounty or famine to the deep. Even the melting of polar ice can ripple down, changing the chemistry of the water and the balance of life. The trench responds in subtle ways. Populations of scavengers boom and bust, following the rhythm of abundance and scarcity. Bacteria and archaea, the invisible architects of the abyss, adjust their symphonies of chemical reactions, recycling every molecule in the ceaseless quest for survival. Some species enter dormant states, conserving energy until the next pulse of food arrives. In this vast and hidden world, every flake of marine snow, every shift in current, every echo of a global event is woven into the fabric of existence. The trench is not a static graveyard, it is a living, breathing ecosystem, forever in motion, forever adapting. Here, in the heart of darkness, life is tuned to the subtle music of the planet, thriving against all odds in the slow dance of change. In the deepest reaches of the trench, knowledge is hard won. Here, conventional eyes and ears fail, the darkness is impenetrable, the pressure immense, and the cold relentless. Only the most resilient machines dare to descend, engineered to withstand the crushing weight and corrosive brine. Far above, silent sentinels hover robotic explorers, their hulls reinforced, their sensors keen. These mechanical voyagers glide through the abyssal dark, mapping unseen landscapes with pulses of sound. Sonar waves ripple outward, painting ghostly images of canyons, chimneys, and towering ridges hidden far below the surface. Delicate arms reach out, sampling the water, gathering fragments of stone, and capturing fleeting glimpses of the trench's elusive inhabitants. Cameras, equipped to pierce the gloom, reveal bioluminescent flashes and the slow ballet of creatures drifting with the current. Remote sensing instruments taste the chemistry of the abyss, detecting subtle changes in temperature, salinity, and the faint signatures of life. Data flows upward through cables or bursts of light, carrying new discoveries to the world above, patterns in the currents, the composition of ancient sediments, the secrets encoded in the DNA of life forms adapted to eternal night. Each mission is a step into the unknown. Machines must endure months of solitude, navigating labyrinths of rock and water, sending back clues from realms never before explored. Sometimes they glimpse the unexpected, a new vent erupting with mineral-rich plumes, a community of life thriving in isolation, or a silent landslide reshaping the trench floor. Through technology's unblinking gaze, the abyss slowly reveals its mysteries. The story of the trench unfolds, not in words or memories, but in streams of data, proof that even in the most inaccessible corners of the world, discovery is possible, and the unknown is never truly out of reach. As we peer into the future of the Mariana Trench, the abyss stands at a crossroads between wonder and vulnerability. Its depths remain largely untouched, a stronghold of ancient mysteries and fragile ecosystems. Yet the world above grows ever more curious, and sometimes ever more intrusive. Emerging technologies promise to illuminate even the most hidden corners of the trench. Next-generation submersibles, autonomous drones, and advanced sensors will map, monitor, and decode the trench's secrets with unprecedented precision. Artificial intelligence will sift through mountains of data, revealing patterns invisible to the human eye. These tools may unlock new discoveries, unseen species, unique minerals, or clues to the origins of life itself. But with knowledge comes responsibility. The trench faces new challenges: the threat of deep-sea mining, the silent advance of microplastics, and the unpredictable impact of climate change. Each could leave a mark on this isolated world, altering currents, chemistry, and life in ways we cannot yet foresee. Global conservation efforts are beginning to recognize the trench's significance. International treaties and protected area proposals seek to shield its unique habitats from exploitation. Scientists advocate for precaution, urging careful study and sustainable policies before irreversible changes occur. The hope is to preserve the trench not just as a frontier of discovery, but as a sanctuary for life in its most resilient forms. Yet the greatest unknowns remain. How will the trench respond to a warming planet? What secrets still lie buried in its sediments and stone? And what lessons might its survival teach us about the resilience of life and the limits of our own stewardship? As the guardianship of the trench shifts from exploration to preservation, the story is far from over. The Mariana Trench endures, a realm shaped by extremes, watched over by machines and protected, perhaps, by our growing sense of wonder and responsibility. Its future, like its depths, awaits discovery.